Alright guys, so today we're going to talk about the gradient and its application for the directional derivative. So I'm going to start first with the idea of the directional derivative, and then we're going to transition into the gradient. And so the idea will be we have a surface, which I drew in blue, so it's kind of, we're not that concerned about it. I want to look at what happens down here more than anything. And so we're going to have a curve f of x naught y naught, which got cut off. I already saw that, but it's okay. And then we're going to have a vector. Let's put a vector that in 2 dimensions. So this is going to be a unit vector u. And since you have a unit vector, you can always relate it to a point in the unit circle. So if you have a unit vector in R2, it's always going to be a point in the unit circle if you anchor it at the origin. So we're going to call this vector just cosine of theta, sine of theta. And again, it's just because I need a unit vector to define this. And so we're going to ask, if I were to travel, or if I were to move on my graph in the direction of u, how much, or what is the instantaneous rate of change of the function? So how is z changing? How is f changing when I travel in the direction of that vector u? And that's going to be called the directional derivative. Again, so the directional derivative then will be given by du f at x naught comma y naught. But for space, I'm going to eliminate the x naught comma y naught. And I'm going to write the definition as the limit as t goes to 0. And then here I'm going to have f of x naught. That's going to be the point I'm located, x naught, plus t cosine of theta, comma, y naught plus t sine of theta. I'm going to have to do it down here because it really didn't fit x naught, y naught all over t. So notice that here what is happening is you are making an increment very, very small, right? And then you're looking at that rate of change. However, the x coordinate, you're affecting it by t cosine of theta. So you're going in basically you're multiplying times t. So you're adding a multiple of this vector to the point x naught, y naught. So you're moving from here and t units in the direction of u. So whenever you take your limit, you're going to be going towards the point x naught, y naught, but in the direction of u. So you're going to be going and getting closer and closer, but you don't care what happens if you go in all the directions. You're only caring about what happens when you go in the direction of u, and of course also from the other side of u, right? Plus minus. So you're going to just be traveling on that line that is given by u. Alright, so that's going to be your definition, but that's not really what we want to write because it seems like it would be way too complicated. So what we're going to try to show now is that in fact this can be computed with the partial derivative, which is going to be the partial with respect to x evaluated at x naught, y naught times the cosine of theta plus the partial with respect to y of x naught, y naught times the sine of the angle. I don't know what happened to my board today. I don't have any room here. Anyways, so we're going to prove that you can do it in that way. So that's going to be the directional derivative. Now, there's another thing that you can actually write. If you just notice this would be also the dot product of the vector fx. I'm just going to write without the x naught, y naught, fy dot the vector cosine theta sine theta, which happens to be actually, you know what, let's call this gradient, the name it should have. This vector is going to be called the gradient of f, and this vector right here is just the vector u that I started with. So the directional derivative of f with respect to u then we'll be able to write as the gradient of f times dot product rather u. However, this one we have to prove that can be written in that form. So let's go ahead and prove that real quick. I'm going to erase here. And then we're going to go ahead and compute an example of the directional derivative. And then I'm going to prove a few properties for the gradient. And I think that's what the video will be about. So let me erase this real quick and I'll be right back. So, all right, so to prove this, what I'm going to do is I'm going to go ahead and write my function h of t to be f of x naught plus t cosine of theta, comma, y naught. I'm going to have to write the rest down here, plus t sine of theta. Am I writing big today? Maybe that's what's going on. And so I'm going to go ahead and compute this derivative. And by the chain rule, remember, because this is a function of two variables, so what I have to do is I have to take the partial of f with respect to x, and then the x coordinate, dx, t, because I'm taking the derivative with respect to t, plus, then I'm going to have df, dy, and then dy, dt. And if I do that, this would just be fx at x naught comma y naught, well, fx of xy firstly. And this dx, t is just going to be, when you take the derivative of this with respect to t, is going to be your cosine of theta. And then here is going to be fy at x comma y, but just to fit everything, I'm going to go ahead and not put in the xy's and take the derivative of the y coordinate. So the y is going to be partial with respect to t, is just going to be your sine of theta. But now what I want to do is I want to, if you write, well, first take the derivative at 0. And so what does that give me? Well, that gives me this fx at x naught comma y naught cosine theta plus fy at x naught comma y naught sine theta. So that h prime at 0 is precisely what I wanted to show that the directional derivative is equal to. But I took the derivative of some random function h. What in the world is that? Well, what would be that h prime by the definition? H prime would be the limit as t goes to 0 of h of at delta t goes to 0, t plus delta t minus h of t evaluated at delta t, or divided by delta t rather. And so if you evaluate what this ht of delta t would basically be having an x naught plus t plus delta t. Now I'm going to evaluate this at 0, right? So I'm going to change this t for 0. This is just going to become delta t, and this is going to become 0. So when you evaluate h at 0, you get this expression right here. When you evaluate h at delta t, or just, yeah, at delta t, you get this expression just with delta t. And then this becomes delta t, limit as delta t goes to 0. This expression is identical to this one, just replacing t with delta t. And so the derivative I computed here at 0 is exactly equal to the directional derivative of f in the direction of u. So that then establishes that, yes, the directional derivative, there's an easy way to compute it by virtue of taking the partial derivatives with respect to x and evaluating it at x naught, y naught, times the cosine of the angle, partial derivative with respect to y, times the sine of the angle. And that then tells you how much the function is changing when you're going in the direction of the vector cosine theta, sine theta. So that's the directional derivative, and the reason why we introduced this gradient, well, it has a lot of applications, but one reason we could think of introducing that gradient is because, well, it now is clear that we can compute the directional derivative by having that gradient. So let's go ahead and erase, and now we're going to talk about some properties of the gradient. All right, so I forgot that I was going to do an example. So let's consider the function first. F of x being xy, f of xy equal to typical one, x squared plus 3y squared. I don't know how many times I've done this graph. And it always looks terrible, but fine. So let's go ahead and remember what the graph looked like. Now let's give ourselves a point here. So I'm thinking maybe a 1, 1. I always give myself the easy ones, don't I? And then when you evaluate this at 1, 1, you get 4. So this point here would be 1, 1, 4. So let's go at that point and let's go in that direction. I don't know, let's take a vector u that is going to be typical point in the unit circle. So 1/2 square root of 3 over 2. And this is a vector, so let's make it a vector. And let's compute the derivative. So basically here we would be going in the direction 1/2. So 1/2 square root of 3 over 2. So it's 2 pi over 3. So kind of in this direction. Not really drawn to scale because this is length 1. Oh, almost. Never mind. So I want to find out when I travel in this direction. So my intuition is that this is going to be going up by a certain amount. So let's go ahead and see what it is. So now that we have the formula, we can do the directional derivative of f at 1, 1 in the direction of u is just going to be equal to the partial of f with respect to x. Partial of x with respect to x is going to be 2x times the cosine of the angle, or the first entry of the vector, if you will, plus the partial derivative with respect to y. So it's going to be 6y times the square root of 3 over 2. And all of that is going to be also evaluated at the point, which is going to be 1, 1, barely fit it. And so when you evaluate at 1, you get 2 times 1 divided by 2 is a 1. Plus 2 times 6 divided by 2, so 6 square root of 3. And it's a positive number, so it tells you that so if you had a line in this direction, a tangent line going on this plane, so if you were to grab u, and you would extend it vertically, so you grab the plane generated by 0, 1, and you draw that plane vertically here, and intersect, then if you were to draw the tangent line to that surface on that plane, then that slope would correspond to a 1 plus a 6 square root of 3. So that's what the directional derivative would tell you, that if you cut the surface, and of course when you cut that surface, you're going to end up having some sort of parabola that intersects with that surface, and the tangent line for that parabola, maybe the parabola would go a little bit further down. The tangent line to that parabola on that plane would have slope 1 plus 6 square root of 3. That's how you interpret the directional derivative. So now let's look at a few properties of the gradient, and I think that would be good enough for us to stop the video. So I'll go ahead and erase, and I'll be right back. All right, so let's return to the idea of the directional derivative being the gradient dot the vector u. Now the dot product, remember, can be written as, so remember the dot product of u dot v over the magnitude of u magnitude of v is equal to the cosine of the angle between them. I'm going to call that angle gamma just because theta I was using for the coordinates of the vector u. It doesn't really matter. So if I multiply both, here I get the magnitude of the gradient times the magnitude of u. U is a unit vector, so it's going to be 1, and then the cosine of the angle between them. So this just becomes the magnitude of the gradient. Magnitude of u is 1 because it's a unit vector, and then the cosine of the angle between them. So now that the directional derivative is given by this magnitude, this is fixed, because at that point the function, whatever the function is at that point, that quantity is fixed. The only thing that is going to change is, well, depending on what you give me, well, the angle between the vector u and the gradient is going to change. So now remember that the cosine is always going to be between -1 and 1. So the maximum possible value for this directional derivative is going to be when the cosine of the angle is 1. But when does that happen? That happens when the angle is 0, meaning that the vector u is going in the same direction as the gradient. Now, of course, it would be, you'd have to normalize the gradient to make it a unit vector. But since you're just going in that direction, then that would tell you that at that point, your directional derivative is maximized when you travel in the direction of the gradient. So that's the first fact. So duf is at a point x0, y0 is maximized and when you goes in the direction of the gradient. And when that happens, by the way, at that point, the maximum value is going to be equal to the magnitude of the gradient itself. Because then the cosine would be 1, so the directional derivative becomes that. Now, the minimum, so the directional derivative is minimized. No, this was an M. Minimized, whatever he wrote there, whenever you have a -1 here. And that is when the u is in the direction, or in the opposite direction of the gradient. And then at that point, the minimum of the directional derivative is going to be the negative of the magnitude of the gradient. And there's one more thing we can talk about is, well, what happens when the gradient happens to be 0? Well, if the gradient happens to be 0 at certain point, then the directional derivative in any direction for that function is equal to 0. And that will tell you basically that if you draw a plane, any vector on this plane is going to have a directional derivative equal to 0, meaning you're on a tangent plane, so you'll have a max or a min, and then that'll be the idea for optimization. We're going to start looking into that next time. I think that's good enough for this video because it's getting a little bit long. All right, well, thank you for watching. This has been fun, and I'll see you in the next one.